Hello, Physics 2 people. Today I'm going to try something a little different. I'm going to try to use the whiteboard space in Zoom. We'll see how that goes. If I feel too constrained with this, I may end up back on the whiteboard, but I'm hoping that it's a little bit more visible and easier for you to see. Okay, I'm just arranging some of the tools and things. Okay, so today we want to talk about magnetostatics. So these are, so this is going to be our first discussion about what causes magnetic fields. So, and in particular, we're going to focus on, you can either say these are constant magnetic fields, or it turns out, because magnetic fields are caused by currents, we're talking about steady currents. Okay, either one will suffice. All right, and the main law that we're going to start with here is the law of Biot-Savart. BiotSavart, the T is silent, it's French, you don't say half the letters. The T's are both silent. So it's not Biot-Savart, Thomas. So it's BiotSavart. And this law will be, it's kind of like Coulomb's law, but for magnetic fields. So it's like Coulomb's law in the sense that it's going to be an integral equation, which allows us to look at the distribution of current and do some sort of an integral and calculate the magnetic field it produces. So here's the thing. This is an experimental fact. You can't derive this. You just have to do experiments to find this. And what you find is the following, that if you have a wire carrying a current, you will find that there are magnetic field lines which encircle the wire. Okay, so they will live in the plane or in the direction perpendicular to the wire in general. So the wire, you can imagine, goes off to infinity. So the magnetic field lines, maybe I shouldn't say plane, but they wrap the wire. That's a better way to say it. Okay. Now this is an experimental fact. You can discover this by, well, one of the ways is if you have a wire with a current flowing through it, just place little compasses around the wire and you'll see that the needle and the compasses will follow the magnetic field lines. If we were in person, we would do exactly that, and then you would understand this. But because we aren't in class in person, I'll show you this little snapshot. So this is a wire. It's carrying a current, although I know you can't see that. And what you see are all of these little compass needles, maybe with one exception here. I'm guessing that's maybe a demagnetized uh, compass, or I don't know, something funky going on with that one. But the rest of them, you can see that the needles of the compass follow along circular paths which surround this wire. So that supports the claim that the magnetic field lines wrap around the wire. As far as how this actually is oriented, you should grab the wire with your thumb. So imagine you reach with your right hand. Ooh, one too many there. Try that again. 1, 2, 3, 4. And align the wire with the current going up. And the way that your fingernails wrap, or your fingers wrap around the wire, I don't know, I guess I'll put dots here. These are your fingertips going into your eye here as we look at it. So the way that you wrap your finger around the wire tells you the way that the magnetic field lines will circulate around the wire. So the magnetic field lines would look, changing color, they would look like they are into your eye over here and into the board, or into the screen on the other side, into your eye here, into the screen on the other side. So again, you grab the wire. This is a mental idea. Arnaldo, don't actually do it. You might electrocute yourself. But the idea is, if you mentally try to grab the wire with your thumb in the direction of the current, the way your fingers wrap the wire will tell you the orientation of the magnetic field. Okay. And you can tell there's a lot of perpendicularity going on here. The magnetic field loops are kind of perpendicular to the wire, at least when it's straight. And there's you're using your right hand. So, okay, don't use your left hand. You get the wrong answer. Excuse me. Okay, so you shouldn't be too surprised with all that there's a cross product involved. And the formula is as follows. So this is the equation version. Okay, and what it says is, let's imagine that I have a wire and it's going to carry a current I, and I'm going to imagine that I'm going to focus on the effect of one little segment here, which points along, so one little part of the wire. And I'm going to ask about the magnetic field it produces over here at this point. Well, the wire, or the current actually, is the source of the magnetic field. So I would say that this vector would be RSO. This is the place where I'm trying to make an observation. So this would be the observation point. And, oh, sorry about that. This point over here, now if you kind of grab your hand in the direction of the current, you'll see that the magnetic field actually has to point into the page over here. All right. So let me switch over to an image I'm going to steal from the internet, and hopefully it's a little bit more clear than my chicken scratches. Oh, sorry. That's not exactly what I want. There you go. That's what I want you guys to see. So the idea is you have a wire and it's creating a magnetic field over here at some other point. Okay, let's go back to our um, whiteboard here. Okay. Now, this little segment is only going to contribute a tiny amount to the magnetic field, so we'll have differential amounts. And if you want the full magnetic field, you have to take account of all the little segments. So the formula is that dB equals, well, there is, see, more current gives more magnetic field, so that kind of makes sense. But it also gets weaker with distance. And the formula is mu naught over 4 pi times the current, so it's proportional to the current, times ds vector cross RSO hat divided by the magnitude of RSO squared. Oh, so this is a unit vector. Don't get confused. I'm going to rewrite this in a minute using the full vector, and then I'll have to make adjustments. ds points along the wire. I is associated with the wire. And this is the vector from the segment, the source segment, over to the observation point. Now, we've got a new friend here. Mu naught is the permeability of free space. It's like epsilon naught, but for magnetic fields. So permittivity goes with electric fields, permeability goes with magnetic fields. Numerically, mu naught equals 4 pi times 10 to the 7th. And the units on this are kind of wonky. It's Tesla meters per amp. Okay. So that's the permeability of free space. Just a number. All right. So we now want to build up the entire magnetic field. So if I have this wire carrying current I, and I want to know what is the magnetic field over here at some generic position, the formula I have is that B is mu naught I over 4 pi times the integral ds cross r hat SO over the magnitude of RSO squared. You know, qualitatively, this looks like so because the numerator is a unit vector, this is like a 1 over r squared sort of dependence, qualitatively, although it's got all this other weird cross product stuff. This is true, this is fine. I oftentimes find that it's easier to work not with the unit vector, but to work with the unnormalized vector in the numerator, and then I have to compensate and adjust the denominator a little bit. So this is completely equivalent to the following. And because I've gone from a unit vector upstairs to a full relative vector, the price I pay is now I have RSO to the 3rd power. That's completely equivalent. I just, oftentimes that seems to be more useful. So, great. So that is the law of Biot-Savart. let's go and apply it to a simple example and um, um, or take it back. In the next video we will apply it to a simple example for a straight wire, and eventually let that become an infinite wire. Okay, I'll see you guys in the next video.